Okay, for what we have in continuing with series, now there is a term that used to be common in statistics books, and you will see this if you were to look into advanced mathematics course textbooks, and we have what is referred to as the binomial coefficient. And by definition, okay, say you're looking for a number of combinations of a certain number of elements, and you're taking so many of them at a time. And we have, by definition, for the binomial coefficient, we have the number of combination of p number of elements taking r at a time is given by, and this p taking r at a time, okay, that is the binomial coefficient. In terms of what we have for how to go about carrying out the operations, well, you're looking at the ratio of the factorial value of the total number of elements divided by the product of the factorial of how many you're taking at a time times the factorial of the difference between the total number of elements and how many are taken at a time. So we have p factorial divided by the product of r factorial and the difference p minus r quantity factorial. And just a quick case, all right, say if you have 5 elements and you're taking 2 at a time, okay, so you have 5 factorial all over the product of 2 factorial times the quantity of 5 minus 2 factorial. So you have, in the numerator, you have 5 factorial, and again, that is going to be the product of the first 5 natural numbers, so that'll be 120. 2 factorial is 2, 3 factorial is 6, and we have 120 divided by 12 is equal to 10. Okay, and I threw in this visual. Let's say if you have like a set of letters where we have like the 5 letters, first 5 letters of the alphabet. Let's say we have A, B, C, D, E. And if I were to take 2 letters at a time, okay, and we have among our distinct combinations, okay, say if I were to take all the combinations that include the letter A, okay, so I have A paired up with B, A with C, A with D, and we have A with E. So you have 4 out of the 10. And then let's say that if I were to take the combinations inclusive of B, okay, that we've not had already. Okay, one might think of BA, but guess what? AB, BA, those are regarded as being the same combination. And in terms of letter pairings, we have not dealt with yet. You have B paired up with C, also B paired up with D, and B paired up with E. And in terms of working with the letter C, well, we've already got AC with CA, BC with CB, and C cannot be paired up with itself, but we do have C and D as well as C and E. And for the remaining combination, okay, we have with the letter D, we already have it with AD, BD, and CD. And for any distinct pairing with the letter D, have D and E. So this is what we have with 2 element combinations, okay, where we have 5 total elements in all. So all of these are distinct combinations. Now, in looking at just evaluating what we have with the binomial coefficient, let's say they have 10 elements taking 6 at a time, and just with the raw numbers, okay, you have 10 factorial has a value of over 3.6 million. 6 factorial is 720. 4 factorial is 24. And you could take the product in the denominator, okay, and so we have the ratio simplifies to 210. This is one way that you could go about it. But for many scientific calculators, okay, the factorial is going to reach a saturation value where for many models it will not even be able to get to 70 factorial. And I don't think anybody would want to write out all the digits of 70 factorial anyway. And there is a simpler way of being able to reduce, okay, and we have with again with 10 factorial all over the product of 6 factorial and 4 factorial, I can take the top factorial number and write in terms of the higher of the 2 factorial values we have in the denominator. And if you notice, for 10 factorial, we have 10 times 9 times 8 times 7. And the rest of 10 factorial is going to be 6 factorial, which we have in the denominator. And so we can cancel out the 6's factorial. And so we have 10,987, which will multiply out to 5,040, all over 4 factorial, which is 24, and that reduces to 210. And other cases of reduction, okay, say we have 100 elements and you're taking 98 at a time. And again, so you have P is at 100 and R is at 98. So you have your P factorial is the factorial of 100. And we have R factorial is 98 factorial. And of course, P minus R factorial is 2 factorial. And I can reduce 100 factorial in terms of 98 factorial and get the 98 factorial to cancel. And so we have 100 times 99, which will be 9,900. 2 factorial is 2. And so this reduces to 4,950. And for what we have in special cases, and this is going to provide a bit of a segue, a little bit of a shortcut once we get into series. Anytime you have a natural number of total elements, and let's say that you have taking 0 at a time, if R is 0, then you're going to have the binomial coefficient, if the bottom number is 0, to reduce to 1. Now, if you have the bottom number to be at 1, okay, that is going to go and reduce to the top number P, okay? And guess what? If the bottom number is exactly 1 less than the top number, then it's also going to reduce to the top number itself. And if you have an identity between the top and bottom numbers, okay, well, that is going to reduce to 1. So these are our 4 special cases. Again, if the bottom number is 0, or if the bottom number and the top number are identical, then the binomial coefficient reduces to 1. However, if the bottom number is 1 or happens to be 1 less than the top number, then that binomial coefficient reduces to the top number, in this case, P. Okay, now for what we have in the case of power series, okay, and let's say that if we have elements X, and we have for all of them, okay, for all elements X such that the absolute value of X is less than 1, we have the power series, okay, where we have 1 plus X raised to the P power is equal to P taking none at a time, and you have times X to the P, and then we have plus P taking 1 at a time times X raised to the P minus 1 power, and we have plus P taking 2 at a time times X raised to the P minus 2 degree, and we have if the series comes to a conclusion, well, we have like the last 2 terms will be the result of taking P minus 1 at a time times X, and you have plus P taking the same amount at a time times X to the 0, and of course X to the 0 is equal to 1, and so is P taking 1 at a time. So for what we have here, so again, P taking none at a time again is 1, so you have X to the P taking 1 at a time again, that goes to P, so that's P times X to the P minus 1, and you have plus P factorial all over the product of 2 factorial and the quantity of P minus 2 factorial times X to the P minus 2. And again, since I don't have the bottom number at 0, 1, or P minus 1, or P, this is not so automatically reducible. And for the last elements, okay, so you have P times X to the first, and we have plus 1 at the very end. Now, let's say that if we have for the determination of power series, where we have a particular power P provided, and say if we're looking at the series expansion of the quantity of 1 plus X raised to the third. Okay, so for what we have, just putting it in the lingo of power series, so your P value is going to be 3, so you have 3 taking none, then you have 3 taking 1 at a time, 3 taking 2, 3 taking 3, and of course we have X to the P minus 1, X to the P minus 2, and we have X to the P minus 3, or in this case 3 minus 3. So 3 taking none goes to 1, so you have 1x cubed. 3 taking 1 goes to 3, and we have times x squared. And again, 3 taking 1 less than itself goes to 3, and you have times x. And then we have 3 taking itself and x to the 0. Okay, they automatically go to 1. So the quantity of 1 plus x to the third becomes x cubed plus 3x squared plus 3x plus 1. Okay, now you can have the x term to be negative and not just x. And say if we're looking at the series expansion of the fifth order of the quantity of 1 minus 2x. And if I put this in terms of series expansion, okay, so you have like what we have had with 1 plus x quantity to the p. I can say I have 1 plus negative 2x, the quantity of negative 2x, quantity raised to the fifth. So the p value is going to be at 5, and that representing x, we have negative 2x. So you have 5 taking none, we have times negative 2x to the fifth, 5 taking 1, negative 2x quantity to the fourth, 5 taking 2, and you have the times the quantity of negative 2x cubed, 5 taking 3, negative 2x squared, 5 taking 4 times negative 2x, and of course we're going to have with negative 2x to the 0, that is going to go to 1. So just looking at the items here, so 5 taking none, 5 taking 1, we had those binomial coefficients reducing respectively to 1, 5, 10, 10, 5, and 1. And for the powers that we have of negative 2x, fifth order, we have negative 32x to the fifth. Then we have 16x to the fourth, negative 8x cubed, 4x squared, negative 2x, and again we have at 1. And taking the product, and we have for the result, we come out for the quantity of 1 minus 2x raised to the fifth, and so we have minus 32x to the fifth plus 80x to the fourth minus 80x cubed plus 40x squared minus 10x plus 1. Now, let's say that if you have some raised coefficients, say if you have 10 minus 20x quantity raised to the third, okay, and I wanted to determine the series expansion on this one. Okay, so if you notice, you don't have the leading term inside the parentheses to be at 1. Instead, we have at 10. So what I can do here is I can just go ahead and factor out 10 and say we have the quantity, or in brackets, 10 times the quantity of 1 minus 2x raised to the third. Okay, and if I separate, so we have conceptually, we have 10 to the third times the cube of the quantity of 1 minus 2x, and 10 cubed is 1,000, and we have times the cube of 1 minus 2x. So we have 1,000 in store, and I can go ahead and obtain the series expansion of the cube of the quantity of 1 minus 2x. And again, so we have the binomial coefficients, got 3 taking none, then taking 1, 2, and 3. And then we had the cubes, the squared, the first order, and of course the 0 power of negative 2x. So you got 1 times negative 8x cubed. Then we have 3 times the quantity of 4x squared, and we have another 3, and then we have times negative 2x, and we have 1 times 1, and we have for the cube of 1 minus 2x, again this goes to negative 8x cubed plus 12x squared minus 6x plus 1. And going back to the original problem, if I take this series expansion and multiply by 1,000, and we're going to have for the final result, we come out to negative 8,000x cubed plus 12,000x squared minus 6,000x plus 1,000. And we will be looking ahead into special cases where we might have non-integer powers.